Science moves fast, like really, really fast. Think about all the new research hitting the servers just today.
It's relentless. And, large language models, LLMs, they're increasingly being looked at as tools, maybe even partners in navigating this flood.
Right, for summarizing, maybe finding connections researchers might miss. The potential seems huge.
Absolutely huge. But there's a big but, isn't there? A fundamental issue.
Yeah, the fact that these incredibly smart models are usually trained on, well, static data, their knowledge is basically frozen in time.
Exactly. So their understanding of science is instantly, well, historical, outdated the moment they finish training almost.
It's like having a brilliant colleague who just stopped reading any journals 6 months ago. Knows everything up till then, but nothing about the latest breakthroughs.
Precisely. So if we want these LLMs to actually help at the cutting edge, they need to do more than just remember old science.
They somehow need to learn the new stuff, right? And crucially, keep hold of the old stuff that's still valid.
And wouldn't it be amazing if they could even, I don't mean, sort of anticipate what might come next, help project future directions?
That's the dream, isn't it? But figuring out if an LAM can actually do that reliably for science, which is so complex and interconnected, that seems incredibly hard to measure.
It is. How do you even evaluate if an AI has genuinely updated its scientific grasp, not just memorized some new sentences?
Well, that brings us to what we're digging into today. There's this fascinating new framework called ScienceMeter.
Exactly. It comes from a paper by Wang and colleagues, and its core academic contribution, really its innovation, is giving us a specific way to measure how reliably LLMs handle scientific knowledge updates.
ScienceMeter. Okay, so our mission for this deep dive, let's unpack this framework. What is it? What makes it different? Maybe more rigorous for science? What did they find when they tested it? And, why should you care if you're interested in AI's role in research?
Sounds good, because ScienceMeter really tries to offer a structured way to look past just checking simple facts. It aims to evaluate if the LLM's understanding of science is evolving reliably.
And it's specifically for scientific knowledge.
Yes, that's key. It's not just general knowledge updates. And its approach is innovative because it looks at knowledge across time, past, present, and even trying to gauge future potential. This multi-temporal view is a real academic novelty here.
Okay, so how do you break down something as complex as scientific knowledge into bits and AI's understanding to be measured against? What are the units?
Right. So the framework uses something they specifically define as atomic scientific claims.
Atomic scientific claims. Okay, why atomic? Why not just, facts or data points like we see in other benchmarks?
That's a really important design choice, and it points to the academic thinking behind it. The researchers argue that simple factoids like, say, a boiling point or a historical date, they just aren't granular enough for the nuance of scientific findings.
Too simple.
Yeah, they don't capture the context or the specific assertion being made in research. So an atomic scientific claim is defined very carefully. It's a verifiable statement about one specific aspect of a scientific entity or process. And crucially, it should be traceable back to a single source, usually one paper.
So it's like the smallest possible unit of discovery or assertion you can pull from a study.
Pretty much. Think of it as the core idea in maybe one sentence or a couple of sentences in a paper's results or discussion. It's about getting precise. This allows the framework to track exactly which pieces of knowledge the LLM gets right, which it forgets, which it messes up during an update. It's about measurement precision, which is academically important.
Okay, that makes sense. Granularity matters for science. So ScienceMeter uses these atomic claims. Now, how does it actually measure that past, present, and future knowledge you mentioned earlier?
That's the core of the evaluation, these three key metrics they introduced. They let you quantify different facets of how the LLM handles knowledge over time. The first one is knowledge preservation.
Right, basically, does it remember the old stuff correctly?
Exactly. It measures how well the LLM holds on to the scientific knowledge it learned from older papers after it's been updated with newer information. You definitely don't want the model learning about, say, gene editing and then suddenly forgetting basic Mendelian genetics.
Yeah, you need that foundation. Avoid catastrophic forgetting, but for science.
Precisely. It's a known issue, but ScienceMeter applies it specifically here. The second metric is knowledge acquisition.
This feels more straightforward, learning the new discoveries.
It is. This measures how well the model learns and correctly integrates the new atomic claims presented in the papers used for the update. Can it actually process and understand recent findings accurately?
Okay, preservation, acquisition. Got it. But that third one, knowledge projection, still feels a bit fuzzy. How can you measure predicting the future?
Yeah, this is probably the most novel and I'd argue the most academically ambitious part of ScienceMeter. Knowledge projection tries to measure the updated LLM's ability to generalize or anticipate related scientific claims that aren't actually in the old or the new papers it saw, but are plausible extensions or connections that might show up in future research.
Whoa. So it's testing if the model can connect the dots, go beyond just repeating facts and actually hint at where things might be going.
That's the idea. The paper argues this projection ability is crucial if LLMs are ever going to be more than just search engines for papers. If they're going to help with, say, generating new hypotheses or identifying the next logical experiment or spotting gaps in our knowledge, evaluating this kind of extrapolation is really new and important contribution of this framework.
Preservation, acquisition, projection. Okay, I see the multi-temporal picture now. But how does ScienceMeter decide if the model actually knows a claim? Is it just right or wrong?
No, and again, this is where the scientific context really matters. It's more nuanced. The framework combines factual accuracy with the model's reported confidence.
Confidence. Why bring that in?
Because think about it in science. An answer that happens to be right, but the model says, I'm only 10% sure. Well, that's not very useful, is it? It could just be a lucky guess, or worse, a hallucination that stumbled onto the right answer.
True. Reliability is key.
Exactly. The paper makes the case that for scientific reliability, the LLM needs to be both accurate and confident. So ScienceMeter classifies the model state for each claim into 3 buckets. Direct, meaning it's accurate and confident. Incorrect, inaccurate, but still confident. And unknown, which covers any case where the model isn't confident, regardless of whether the answer was technically right or wrong.
Oh, so if it hedges its bets or says, I don't know, it's marked unknown.
Yes, lack of confidence means unreliable knowledge in this context. And this setup directly leads to the 2 main error types they track, which is another key academic distinction: loss and distortion.
Loss versus distortion. Okay, what's the difference?
Loss is when a claim the model should know, either old stuff it should preserve or new stuff it should acquire, ends up in that unknown bucket. Basically, the model forgot it, couldn't retrieve it, or just wasn't confident about it. It's a failure to recall or learn effectively.
Okay, that's bad, but maybe understandable. What's distortion?
Distortion is the really problematic one. This happens when a claim the model should know is classified as incorrect, meaning the model gets the fact wrong and it confidently states the wrong information.
Confidently wrong. That does sound worse.
Much worse. And the ScienceMeter paper makes a strong academic argument here. Distortion is significantly more dangerous than loss in a scientific setting. A model saying, I'm not sure, is suboptimal, that's loss. But a model confidently asserting something false that can actively mislead researchers, propagate errors, destroy trust. Quantifying and highlighting this specific error type is a major contribution.
That distinction feels critical. It really hits at the core challenge of trust